Hi there, welcome to another vintage computing video featuring the Heathkit H8 computer. My H8 is sitting right next to me here on the bench, counting away. Now this display here is an octal, so you've got the memory address and the value of the data in that address. You can see the value of the data is incrementing. We'll get into how that works in a bit. But what I wanted to talk about to start with is the CPU board that this computer has. And as shipped from Heathkit, this would have included an 8080 CPU featuring the Intel 8080 microprocessor. That would have been what would have been used back in that particular vintage of computer. And the 8080 was very popular CPU back in that time period, used in a lot of both commercial computers and kits. And it's likely that if you buy an H8, it will include that CPU. Now, people have produced various upgrades for this computer. For example, in one of my recent videos, I designed an 8085 CPU board for it. The 8085 supporting a little bit higher clock rate than the 8080 and being a little bit newer microprocessor. Other people produced boards with a Z80. I even came along and did a Z8000 16-bit board at one point just for fun and to try something obscure. But I wanted to explore with this, what if we go in the other direction? Rather than going to a newer microprocessor, let's try going to an older microprocessor and seeing if we can get the older processor to do something useful. And I think the natural choice is to go from the 8080 way back to the 8008. Yes, the 8008, a very early 8-bit microprocessor. And that is what is running in here right now in this CPU board in this computer. So what I'm going to do in this video is I'm going to talk about the CPU board that I designed to use the 8008, and I will talk about some of the complications and challenges of moving to an earlier CPU, one that might have lesser features or lower clock speed than you started with. It's actually quite challenging to do that. Had to completely rewrite the panel monitor in here and rewrite all the display refresh stuff because the instruction set was different. So we'll talk about what went into doing that, as well as demonstrate some of the things that I'm able to do on that. Okay, let's go ahead and do a quick demo of the front panel. Now I've currently got it off. When I turn it on, it's going to take a second or two before the display comes up, and it's not actually loading anything. What it's doing is spewing a bunch of output out the serial port. And the way I've implemented this is that it services the front panel during the serial input routine. So while it's waiting for serial key presses on its monitor, it'll go along and it'll service the front panel. And I've done it that way because I am not currently implementing interrupt-driven front panel service routine on this. I am doing it all via polling. And we may talk about later in the video some of the challenges I had with interrupts and why I chose to do it that way. Let's go ahead and turn it on. So there it is, it's up and running. Now, as I mentioned in the beginning, the front panel display, I had to rewrite that part from scratch. The 8008 is not instruction set compatible with the 8080, so none of the original Heathkit software works with that particular CPU board. You're kind of back to square one with software. So it's a good Saturday project to sit down, learn 8008 assembly, and write a front panel monitor. And that's what I've got here. So when it booted up, it automatically went to address 037333. That's an octal. And that is where I have a counter set up that counts the front panel refreshes. So this panel, this is not a set it and forget it type display. This is constantly being refreshed. So the panel wants to be refreshed about every 5 milliseconds. So every 5 milliseconds, you hit another digit. And if you see any flickering, I don't know if the flickering will be visible in the camera or not, but if you see any flickering, that's because, you know, it's doing every 5 milliseconds, doing digit, 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 you know, on, and then it cycles back. And it does, occasionally it does some computation, and occasionally it'll check its keypad. But right now it's looking at the second byte of a 32-bit counter. We can go backward. That's the first byte. You know, this is counting the 5 millisecond refreshes. You can see it's going by faster than you can read it. We've got the second byte there. The third byte, you know, we're getting toward the more significant byte, so it's going to be a while before this one sees an increment, and then, you know, we'll have a fifth byte or a fourth byte if you let this sit here and run for a long time. You can see other stuff in here, like here's my digit refresh. So this is telling it which digit to hit on the display. It's just kind of a scratch work area for the monitor. The Heathkit panel monitor has the same sort of thing in it, so I kind of intuited what they did and wrote my own. So you can move around in memory. We can enter an address, so everything is an octal. When you go to enter an address, it'll light up these dots down here to let you know you're entering an address. 111-222, a good enough address, and it has a value of 162 octal in it. And again, you can go back and forth here. Now, if you want to alter, there's an alter button. Push that, it lights up these 3 digits. This is a little bit different than the Heathkit monitor, which the Heathkit monitor, to let you know you're in alter mode, it would oscillate the decimal points across. That just took too much CPU for me to do that. So this CPU is only running at 500 kilohertz. So we're having to do all this display refresh, on a CPU with a 500 kilohertz clock. So it's a little bit slow. So if we wanted to put a value in here, like let's put the value 333. And it automatically increments to the next spot. So go back. There's our 333. And here, let's put a 222. So we're just blowing away whatever's in memory in these RAM locations. So that's alter mode. Here, cancel to exit alter mode. So it doesn't do registers like the Heathkit monitor would do registers. This one doesn't do registers because it's a little bit lesser feature set. But I did implement the ability to do I/O ports. So similar to how the H8 does I/O ports. So let's write a value to port 9. So we'll put in an address. We'll output the value 123 hex to port 009. Sorry, I forgot I'm in octal. So let's try that again. Value 123 to 0. Would it be 1 1? That would be 9 in octal. And then if we push the out button, move the camera up just a hair. You should be able to see right across here, there are some LEDs that are not lit. So if I push the out button, we should output onto those LEDs. There we go. So that's octal 123. And then similarly, if you want to do inputs, I've got a little dip switch set up here that we can play with for inputs. Let's use address. I think that should be port 8, so it should be 010. So again, 000, 010, and let's hit input. So it read a 363. Let's just squirrel up the dip switches here. They're high by default. 003, and we can scroll them up to something else. 063. So there. I mean, that's basically all my little panel monitor does. It allows you to examine memory and to change memory and to read and write the I/O ports. Now, when I started this project, I looked for existing resources out there in the web, and I came across a couple of them. The first one here is this one by Jim 11662418. Jim Luce. So he has an 8008 SBC that looks like it has been in active development. He's been committing changes to it as of a couple months ago. And here's a picture of Jim's computer here, mounted on this nice proto board. And he actually goes through a great job of going through the various segments of the design. So it's very easy to follow this and just look at each piece in and of itself and understand each functional subcomponent of it, whether it be CPU, memory, or the logic in the GALs. So he happened to use GAL22B10, which happens to also be my programmable logic device of choice, and used a simple bit bang I/O. So the serial I/O just goes out a couple of buffers and latches here, and just goes out to a max 202 or similar chip, and you do your timing manually in the CPU. So a little output ports and power supply circuitry, it's all here. And if you wanted to produce a simple single board computer, this would be a great starting point. And Jim also has code in here for many applications. So he ported Selby Basic, he wrote a monitor, and then he's ported some other 8-bit assembly language programs like Galaxy, which happens to be very much like Star Trek.
Another one is this 8008 computer clock by Len Boyles. So this one here is also just a treasure trove of useful information, dives into the design. And one of the nice things here is he actually talks a lot about interrupt processing. So that was one thing that I struggled with a little bit in my design was what to do to try to support interrupts. And in here he has a bunch of schematics, and you can follow out the various basic design here for this one as well. So between these two other projects here, I was able to learn quite a bit about the 8008. I was able to borrow a fair bit of code and chunks of schematics and some PLDs and such, used as a basis for my own project. Okay, taking a quick look at the datasheet for the microprocessor itself. The datasheet's easily available online on many sources, including BitSavers. You can see here that it's actually, let me zoom in, it's actually a fairly physically small chip. It's only 18 pins, and 8 of those pins are the data bus, which is actually triplexed. So sometimes it is a data bus, sometimes it is the lower 8 bits of the address bus, and sometimes it is the upper 6 bits of the address bus, plus a couple control bits. So you get a lot of use out of those 8 pins. There are 3 state bits here. These will kind of tell you what is going on, which T state you're in, and the T state will tell you which one of these things you're multiplexing onto this 8-bit bus over here. So a particular state will say, hey, you're doing the lower 8 bits address out, and then that's what will be present over there. There is a 2-phase clock that goes into this, a 500 kilohertz 2-phase clock. There is an interrupt signal that can be used to interrupt the CPU, and a ready signal that can be used for dealing with slower memory. Now, powering it is a bit of a challenge because it actually runs on 14 volts between the VCC and the VDD. Now, what most people do here is they will supply 5 volts to the VCC and minus 9 volts to the VDD. That gives you your 14 volts while also being compatible with standard 5 volt TTL logic. You can get the information on those T states here, how you decode the state bits to the T states, and down here into how the T states lead to, what goes on that 8-bit bus, whether it's the lower address, the upper address, or the data in or out. It will also talk in here a little bit about interrupt handling. Here's cycle coding. This tells you whether your operation is a read of the instruction, a read of memory for something other than an instruction, a write of memory, or an I/O operation. Going down in here. Okay, let's talk quickly about interrupts. So an interrupt comes in, it will acknowledge it by putting a certain state out on those state bits, which indicates a particular T state, which is interrupt acknowledge. Then when you see that interrupt acknowledge, you'll get the opportunity to jam in an instruction on the next memory read cycle for the instruction. Now you could choose to jam in something like a NOP, which would do nothing, but you could also jam in something like a restart instruction. Restart is like kind of like a software interrupt vector in that it just causes a jump to a specific location in lower memory, which you might have a vector that jumps you somewhere interesting. The restart is actually a call, so it will actually push an address onto the stack, which you can return from. This would be your standard way of doing an interrupt service routine. Not a whole lot different from what the 8080 does or the 8085. But the problem is with the CPU, what you're lacking is any kind of push or pop instructions. And this, while the CPU does implement a stack, it's actually the stack is implemented on the CPU rather than memory, but it does implement a stack. It will push the program counter on the stack, but there are no operations to push the registers on the stack. So if you're an assembly language programmer and you've written interrupt service routines, you probably know that the first thing you do in an interrupt service routine is to push the registers that you're going to modify so that you can return from the routine without having messed anything up. You can't actually do that here because there's no push or pop operations. Now, you can't even write them to main memory to save them unless you're willing to clobber a couple of registers, because the only way to write a register to memory is by first putting the address that you want into the H and the L registers. So all of this makes it somewhat difficult to write interrupt service routines. And there are options around that. There are projects out there where people have implemented an external general purpose stack attached to an I/O port. That might be one of my next iterations in this, but for now, I just decided that because of this, I'm not going to really fuss around with interrupts. The next thing I wanted to talk about was the input-output instructions. So lots of microprocessors will implement I/O ports that are separate from main memory and give you dedicated instructions to use those. So the 8008 is no different. It does include those instructions. It's got an INP and an out that will read and write those ports. And it'll do that with special states out there so that you can know that you're doing an I/O read or write instead of a memory read or write. But one of the things that is limiting in this is that there are only 5 bits available total for the port. Usually when we're using some of our more modern microprocessors, we're used to 8 bits, at least, sometimes even 16, but at least 8 bits, giving you 256 different ports that you can read or write from. Here we only have 5, and they're further subdivided between input and output. So the input instruction only has 3 bits in it to specify the port number. So just by virtue of the instruction set, you can only have 8 different ports that you can input from. Now the out instruction has all 5 bits here, but the top 2 bits cannot be 00. So this would normally give you 32, but remove everything where the top 2 bits are 00. This gives you 24 ports that you can write to. So you can read from 8 ports, you can write out to 24 ports. That will become important as we're going through the design in the next segment of the video, because it's going to influence how we talk to devices on the H8 bus. Okay, let's take a look at the schematic. Now, the schematic runs about 5 pages long, so I'm not going to go through every page in excruciating detail. I'm just going to kind of give you the highlights of it. And this is the first page where we have most of the CPU stuff. So first of all, right here is our CPU. Zoom in a little bit so we can get a closer look at him. So what we've got is the 8008 CPU. It has that triplex bus. By default, the bus is pulled up to plus 5 volts via 10K resistor. And then, on my project is just about the same as everyone else's. There's some of these drivers associated with it. So there's this bidirectional buffer, this 74HCT245. So there's a direction bit which will tell you whether we want the data going out or the data coming in. That will give you your data bus. And then there are 2 latches, in this case 74HCT273s, that latch the lower 8 address bits or the upper 6 address bits and the 2 control bits. And there are some signals that will tell it when to do those ones. Now we need to discuss all of the control stuff and the clock stuff. So with that, let's start with the clock. Clock is relatively easy. And over here, we have a pair of oscillators. And I did this because the Heathkit H8, it needs to have a 2 megahertz clock for its front panel to handle the front panel refreshes. So I knew I needed a 2 megahertz clock. Actually, 2.048 megahertz, I think, is what it's supposed to be. So that goes there. This signal will actually go out to the H8 bus here. And it can go into this 4040 divider where it is each one of these successively divides into. So you divide it in half, you'll get about a 1 megahertz clock here. Divide it all the way by like 2 to the 12th, and you would get, I believe this would be a 5 millisecond clock down here. This was going to be my attempt to simulate the front panel interrupt in the case where you don't actually have a front panel. So kind of forget about that, forget about this down here and just pretend this is just a simple divide by 2 to get you that 1 megahertz. Now, in the case you wanted to go with a different speed and you wanted to overclock, I'll just put a footprint there so you can run a different oscillator. Now, to get the actual clocks to drive the CPU, you need a 2-phase clock. And that goes through this flip-flop, which divides it in half and gives you 2 alternating signals, Q and not Q. And then it goes through this 74HCT02 that combines it with the clock signal here. So you end up with a 2-phase clock that you can send to the CPU. This clock phase 1, clock phase 2. You can read Jim's GitHub page on his project, and he'll talk a bit about the clocks, or the one by Len Boyles, I think, may talk about the clocks as well. This is not, strictly speaking, compliant with the datasheet. The widths of the pulses are a little bit off, but other people are using this. It seemed to work, so I went ahead with this circuit. Um, Now, Jim in his project, he actually used one of these PLDs instead of using these two 74 HCTO2 gates. I just ran out of space in the PLDs, but you can still see I've got some remnants where I'd plumbed a couple signals over here into the PLD with the intention of using them. Put solder jumpers so I don't have to use them. I did run the clock phase 2 into this. So the first PLD is this bus controller PLD, and its primary job is to take those three state signals, SO1 and 2, as well as the two configuration bits from the upper address latch, CC1 and CC2, that tell whether you're doing instruction fetches or memory writes, memory reads, and the sync bit. Take all of those, munge them together, and generate the timing signals for the rest of the ICs here. I used an MCP 130 as my reset circuit. I use that on a lot of my projects. It's a supervisory IC, monitors the voltage. Once you get up to 4.5 volts, it takes the CPU out of reset. You can also push a button to reset, or you can use a header to reset. That goes into this flip-flop here, and this flip-flop is used to indicate when a power on reset is occurring. And it does that by using the reset to preset the flip-flop, and then the S0 state bit in order to clock in a ground to reset the flip-flop. And you get a couple states out that are both power on reset, one of them an active high, one of them an active low. Power on reset also used to clear these two address buffers to zeros so that we're pointing at the 0th instruction. So this next PLD here does a bunch of address decoding. Now, I'm not going to go into this in a bunch of detail. If you want, you can open up the PLD files and look at them. But just know that it takes IO read and write. It takes a bunch of address bits, and it tells which devices we're reading and writing from. So there's some onboard devices decoded by these various 2 to 4 and 3 to 8 decoders. There's some external devices that'll be on the H8 bus. Let's zoom out here. So the H8 bus, so you've got a bunch of connectors over here. These are the H8 edge card connectors. There's actually 3 sets of them because I have 3 different kinds of connectors that can hook up. So just pretend, one set doesn't exist, the other does. It's a 50-pin connector that connects the board to the H8, and all of its signals will go through these other buffers. So there is an address buffer where we take the address signals and we send them out onto the H8 bus. H8 bus uses inverted logic, so we have to invert all of those address bits and we dump them out on the bus. I'm only doing the lower 8 address bits, so I made the decision with this board that I was not going to put memory out there on the H8 bus. I would only put I/O devices because there's just really no reason to put memory out there. We can put all the memory on the primary CPU board here. So that does the lower 8. The upper 8 address bits, I just hooked them to a pull up to 5 volt. Down here we have some buffering on IO read and IO write. Again, those need to be inverted. Memory read and memory write, I plumbed them through even though we're not supporting memory. The simulated M1 signal, the clock, it hooks up to that 2 megahertz oscillator. Buffer that, inverted or not inverted. There's some jumpers to let you choose here. And then I also borrowed, this last one is just me borrowing a gate for something else. Don't pay attention to that. Over here, we have the data buffers. Again, we're just doing port I/O. We're not doing memory I/O. So you have one buffer that is going to be the outputs from the CPU to the H8 bus, and the other buffer is going to be the inputs from the H8 bus into the CPU. Now, it's kind of weird here. People look at this and say, well, why are you buffering these address pins? Well, that's actually how the 8008's output instruction works. It doesn't put the output data to the port on the data bus. It puts on the lower 8 bits of the address bus. Kind of strange. I'm sure they had their reason for it. It probably had to do with, optimizing chip count or something. But just know that you do a port write, you're using A0 through A7 and sending those out. You do a port read, you're reading them in through D0 through D7. And then there's a couple of these signals connect to that I/O PLD that tell it when to activate the read and writes. Now, if you remember when I went over the CPU at the very beginning, I said that one of the limiting factors of the 8008 CPU is it only has 8 input ports and 24 output ports, whereas the H8 bus, of course, has 256 ports, and you can hang a whole bunch of I/O devices off of that H8 bus. So it wouldn't be feasible to limit yourself to only 8 and 24. So what I did is I implemented an I/O port mapping system here, where we take and we have map registers, just like how people do memory mapping, do it with I/O mapping. So what we're going to do is we're going to take 3 bits. So you recall the input instruction had 3 bits, so it could do 8 ports, and the output instruction had 5 bits, so it could do 24 ports. We're going to take 3 bits. We'll get those off of A9, A10, and A11, and we're going to use those 3 bits to multiplex all 256 possible ports on the H8 bus. We're going to use these 4x4 register files to do that. And this is a technique that I borrowed from people who do memory mapping, particularly on the CPM retro computers. They'll use these 74HCT 670s. And what we can do is we can write an address to these that will tell how the mapping goes. So you can set up a mapping such that, for example, when IO port 0 on the 8008 maps to port 247 on the H8 bus, for example. The easiest way to see this would be to look at the README file in the repo or look at the code, and you'll see where it sets up these mapping registers. But just know that this allows us to map any of the H8 computers' 256 input and output ports into the just 8 input and output ports on the 8008. And we'll just have to set them up. If you want to talk to the serial port, make sure you configure these things to point to the particular H8 port for the serial port. If you want to talk to a different port, you can configure them for something else. Page 4 is memory. So I put in two 32-pin sockets. Now these allow us to put in fairly large ICs. We're only going to use 32K of this one, so an AS6C 1008 is fine. I think the pinout might actually be compatible with the 62256 for the RAM. The RAM has a memory read, memory write, RAM chip select. This one here, for the ROM, I've designed it so that you can use a 39SF040, a 39SF010. Those would be 128K and 512K flash memories, respectively. And that's a lot. Or you can use a 28C256 or a 28C512. Those would be 32K or 64K memory, like EEPROMs, respectively. And just by putting the right jumpers in the right places, you can use whatever ROM chips you have on hand. I've been using a 28C256, which gives me 32 kilobytes. And if you had used one of the bigger ones, and there's a dip switch here that you could use it to select the upper address lines on this, and you could put several different programs in your ROM and be able to flip between them with dip switch. Now I went ahead and I also implemented a memory mapper down here. The memory mapper is optional. So there's 3 jumpers here. If you put all 3 of them to the left, pins 1 and 2, then the memory mapper is disabled. And the board will only segment the memory into 8 kilobytes of RAM and 8 kilobytes of ROM. If you put all 3 of these jumpers on pins 2 and 3, then you have a general purpose memory mapper here where you can take 4K pages of address space. The 8008 has a 16K address space, so that's four 4K pages, and you can take those pages and arbitrarily map them to 4K pages in ROM or RAM. And you can use up to 32K of ROM and 32K of RAM that way.
Okay, let's take a closer look at the board. So the first challenge is, can you spot the CPU on this board? Usually we're looking for one of the bigger chips. You're looking for like a 40-pin dip someplace. Maybe you think it's like one of these big guys up here, these 32 pins, but no, it's this comparatively small size one right here, this 18 pin 8008 CPU, kind of hidden down there in kind of the bottom middle of the board. So there's your CPU. We have a clock to drive it. I've got a 2 megahertz oscillator, which is that goes to the H8 bus, as well as going through the clock divider chip here to get a 1 megahertz where it goes into a flip-flop and generates the 500 kilohertz two-phase clock. We've got our PLDs over here. So there's the bus PLD, the IO PLD, the interrupt register PLD. I have not implemented the interrupt controller PLD yet. I'm saving interrupts for kind of an advanced point in the project, maybe next time. So up here I have an AS6C 4008. It's a relatively large 512 kilobyte RAM chip. We only use 32 kilobytes of that, but just for the sake of using parts that I have in inventory already. And over here we have a 28C256 electronically erasable EEPROM, so an EEPROM. And that is a 32K part, and that has our four banks in it that we can store 4 different programs in. We have the H8 bus connector over here with its various buffers for the data are down here. There's a pair of them for the data, one for the address, one for the control lines. And there's a 8-bit output port up here hooked to these lights. There's a 4-bit input port. We have the BitBang serial port is sitting over here on this header, as well as this MAX 202. Talk a little bit about the power circuitry. So up here we have a Pololu switching regulator. We get our 5 volts, so 8 volts comes in off the H8 bus. It's brought down to 5 volts. For the minus 9 volts, as I mentioned, there are 2 options. So you could use a 7909 linear regulator and run it off of the minus 18 volt supply on the H8 bus. It's kind of a lot of delta to be soaking there in that thing. Might throw off some heat. Or you can use a little DC to DC converter to take the plus 5 and turn it into a minus 9, which is what I did in this case here. And you know, that way you can hook it up to this jack here, and you can actually run this thing as a single board computer from a single 5 volt out the BitBang serial port without hooking the rest of an H8 up to it at all. And that was helpful in the initial trying it out and such, just to be able to plug it in as a single board computer. Okay, let's take a look at the serial interface. So what we're looking at right now is a dumb terminal that I have hooked up to this. It actually uses the Microsoft Propeller VGA terminal. So if I hit Control F10, you know, you can see these are my terminal settings. We're basically talking at 2400 baud. To the H8 computer via the H8 serial board at 16450 UART and into the 8008 CPU board. So I'll hit the reset switch on the H8, you know, and as you can see, this is what it comes up every time it resets. So I started out with this, as I mentioned before, with Jim Luce's project, and he had already written a serial monitor. So I borrowed most of the code from that for my own. So a lot of these functions in here, you know, the call subroutine, the dump RAM, all of that is right out of his monitor. And, you know, I modified it for my H8 project. So, you know, we can do some things like dump 0100, you know, and it dumps out some of what's in RAM. You know, you've also got the ability to change some memory, 0100 and 1 2 3 4 5 6. You know, we can just start changing memory. You know, it does the typical things. You can in and out bytes to ports. You can jump to an address. He had a really nice thing in his monitor, which was this hex file download. So this uses the Intel hex file format, and you can download an arbitrary program to RAM, and you can run it. But what I've done is, to support my memory banking scheme, I've added a few extra things. So first of all, there is this S down here, which will switch to an arbitrary bank and load it from ROM. There's also a B for basic command. And the B for basic is just a kind of a shortcut. So let's go ahead and go into basic. You can see it loads up here, and it's based on CellB basic, CellBal. this LB Basic interpreter, and this was originally another port by Jim Luce, so he had modified it for his single board computer project, using the BitBang serial port, modifying it to use with the AS assembler, etc. So I used his port of it, customized it for myself, doing such things as making it work with the 16450 UART in my H8. So you always have to start by doing SCR to erase the memory. This particular basic interpreter doesn't erase it himself. And then let's type in a statement. And then we can run it. Scott was here. Let's see if we can make it a little bit more complicated. For I to 10, and then 40, next I. That ought to work. What do you think? So as you can see, not necessarily the fastest basic interpreter in the world, especially running on 500 kilohertz CPU, but quite functional. And you could if you were just starting out with computers, you could write yourself a basic program. This would really be a pretty big deal to you back in the time. Let's go back to the monitor. I'll hit reset. There we are, back in the serial monitor. Now you can switch, because of the way I've set up the memory banking. You can have 4 different 8K images. So image 0 is the monitor. That's the one you load by default. Image 1 is basic. We've seen that. That's the same as hitting the B key. But the way I set this up, you can put whatever you want in the other two images. So image 2, I put in a Star Trek game. So yeah, I want to go on a space voyage. Okay, so there we are. And I've been a long time since I've played this, but let's what do we do? 0 course. See, I don't even know which way the courses go. Let's, I don't know, 6.0, warp factor 1.0. I moved out of the galaxy. My ship is lost. So that must have not been a good course. Let's try this. Can we do? Oops. 1 is scan. Let's do. I don't know. Course 4.0. 1.0. I also moved out of the galaxy. Well, I am going to have to learn how to play this game. I can hit no. And then it just goes, it halts the CPU at that point. You don't want to play. Okay, I hope you enjoyed this video on this 8008 CPU boards. This was a pretty rewarding project for me. I got to go way back in time, back before I ever even started with computers, and experience a CPU that was really at the forefront of the computer revolution, the 8008 CPU. And not only did we manage to build a useful single board computer here, but I installed it in the H8, and we got to use the H8's front panel, and we got to use some of the H8's peripherals like the UART, and we could really show off how this thing would be useful in a general computer scenario. So again, I hope you enjoyed, and I'll catch you next time. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.